A geometric series is just a fancy way to talk about the sum of the terms of a geometric sequence. We could generate a bunch of these terms and add them up by hand, but it can get quite long, especially when you're talking about doing it for like 10 or more. Then it gets pretty tedious. So thankfully we have a formula for the sum of the first n terms, finite n terms. The geometric sequence has to have a first term that's known and a common ratio. Of course, that's what makes it geometric. And then the sum of the first n terms is the sum of the first n terms, Sn, the sum, sigma, as I goes from 1 to n of a1r to the n minus 1. You'll notice that notation is just telling us that we're adding up these terms of the geometric sequence that are defined by this nth term formula. Is a1 times 1 minus r to the n over 1 minus r. And this holds as long as r is not equal to 1. Of course, if r was equal to 1, we wouldn't have a very interesting geometric sequence. It would just be that number again and again and again times 1. So generally, we don't run into that situation. In number 56, we can identify these pieces. We see that n is 10. That's how far we are going, how many terms. Rather than write them all out, let's identify the pieces and use the formula. The first term is what happens when n equals 1. And so when n equals 1, we get 3 halves to the 1 minus 1, which is 3 halves to the 0, also known as 1. So this guy down here tells me the starting point in the first term. So in this term, the first term is 1, or you can think of like a secret little 1 in there. So we have the first term, we have n, we need the common ratio r. We see that common ratio r is this thing, the guy that got raised to the power. So the common ratio r is 3 halves. And we can use the formula. The sum of the first 10 terms, Sn, S10, is a1 times 1 minus r to the 10 divided by 1 minus r. Now we know what a1 and r are, so we'll put it in. a1 is 1 times 1 minus r, which is 3 halves, raised to the 10th. So that's all 3 halves raised to the 10th divided by 1 minus r, which is 3 halves again. This gets a little tricky for students in their calculators. We really want 1 minus 3 halves to the 10th divided by 1 minus 3 halves. Of course, you could do the 1 minus 3 halves in your head probably, or off to the side, but it's a little unlikely given people's affection for fractions. So let's see what we can do in our calculator. Probably all of it. 1 minus, I want to multiply all of 3 halves, or raise all of 3 halves to the power 10, and have that be the numerator. So notice that those parentheses indicate for me that I have one giant numerator right here. And then we'll divide by this denominator with another set of parentheses. So divided by parenthesis 1 minus 3 halves is 113.333, but WebAssign will say, hey, I don't like this thing as a decimal place, so we want to turn it into fraction. Let's see if we can math number 1 to fraction, and she can do it. So I got 58,025 divided by 512 by using the calculator. If your calculator isn't that powerful, do the top, 1 minus 3 halves to the 10th, and you get that number, and then divide it by the bottom, 1 minus 3 halves, and get that number, and that should help you make the fraction, and then reduce it if you need to, if everybody's a factor of 2 or something. So again, same type of formula, number 60. Alright, we have to identify the pieces. We have n equals 12 for the finite sum. The first term is 16, and the common ratio is 1/2. So the sum of the first 12 terms is the first term times 1 minus the common ratio raised to the n power of 12 divided by 1 minus r is the first term 16 times 1 minus r is 1/2, raise it all to the 12th, and divide that by 1 minus 1/2. So all this is, remember, extra parentheses up here and down here. So parenthesis in the calculator, parenthesis 16 times 1 minus 1/2 needs another parenthesis because we want to raise the whole thing to the 12th. And then divide by excuse me, 1 minus 1/2. Again, ugly decimal. I want a fraction, so let's see if she has the power, and she does. For 4095 divided by 128. So that's how WebAssign will want it, as an exact fraction. Again, if you can't get there with your calculator, do the top and then do the bottom and make the fraction yourself. These series can also be infinite, as scary as that might sound. We saw some examples in chapter 9.1 of infinite geometric series that did in fact converge to a finite sum, even though we were adding up infinitely many terms. This is a particular case, and it only happens as long as the common ratio is less than 1. Then each subsequent term is smaller than the one before, so we can be approaching one finite sum. So we can write that as the sum of the geometric series, the sum from n equals 0 to infinity of a1 times the common ratio r to the n power. This is the same thing if we change the index, and you might see this also from maybe I equals 1. So now we start at 1 instead of 0, still go up to infinity, still start with the first term a1, but raise the common ratio to the power I minus 1. Of course, I and n are interchangeable. The important thing is that when you start here at 1 or at 0, the first term of the series is a1. So that's an important thing to notice. If this is the case, if we meet this criteria that the absolute value of the common ratio is less than 1, so it's a small common ratio, like a fraction, like 1/2 or 2/3, then the finite or the infinite sum converges to a1 1 over 1 minus r. Believe it or not. This is quite simple, even simpler than our previous example. So for 76, it's an infinite sum. The first term is 4. The common ratio r is this thing that gets multiplied to a particular power, is 0.2. You'll notice that the absolute value of r, the common ratio, the absolute value of 0.2 is 2 over 10, or 1 over 5 is all less than 1. So we're in good shape. We can apply this idea that the sum is the first term divided by 1 minus r. The first term is 4. Divided by 1 minus 0.2 is 4 divided by 0.8, or 5. So this series converges to 5. Even if we were to write out 1,000 terms, we'd only be getting closer and closer to 5. For 74, again, it's an infinite series. It has the general picture that it's a1 times r to the n. N starts at 0, so when n is 0, the first term, a1, is 1. The common ratio r is negative 1/2. excuse me, the absolute value of this common ratio is less than 1. Absolute value of negative half is a half, so that means that we can apply the theorem or the formula that the sum of the infinite series is a1 divided by 1 minus r, where a1 is 1 and r is negative half. So 1 divided by 1 minus 1 half is 1 divided by 1 plus 1 half. So 1 divided by 3 halves is 2/3 for the finite sum of an infinite series.